This was inspired by something I saw on the internet, yes, but the answer was dead wrong. And so I'm going to rephrase the question in such a way that you cannot interpret it wrong. Because what they gave as a solution, I'm not going to write it down, I'll give it, I'll verbally tell you. What they gave as a solution, as the person who said, well, this is the answer, the way they verbalized it, yeah, but it was kind of a BS answer. So I'm going to state it slightly differently. Using 3 straight lines, draw a square. You can do it on this paper right now. Using 3 straight lines, draw a square. Yes, it is possible.
Can I use the paper as a...
No. So you can figure it out. There is an answer. I gave it to high school kids last night. They hated me when I gave them the answer. While you're thinking about that, which team's going to go first? Let's mix up the order. If you went first and second, third, fourth, you have to go in a different order from last time. Okay? That could be a one-team shift if you want. And everybody shifts down. But we're going to do a different order. The other thing is you will be writing your assessments of you're going to provide a review for each team. You will submit that Friday. I will create the turn-in submission for that. I will be grading that.
Professor, can we go first?
That would be draw 3 lines in a square. And the original question that I saw on the internet was draw a square with 3 lines. And I'll give you the answer that the person said was the answer, and I go, yeah, that's kind of BS. Draw a square with 3 lines.
Yeah.
That's not it. Because that's kind of a BS answer. My answer when I give you the, so that's why I changed the wording a little bit. Using 3 lines, draw a square. So that can't be part of your answer.
Can we go first?
Sure. Charles, can you go first?
Yeah.
Yeah. Okay. Charles is first. Who's second? Team 2 is going to go second. All right, 2. Who's 3?
I think we're kind of forced to take 3 because we went 4th last time. But we're still waiting on team members.
And
Andy's going to pull over. So
I know. Okay, who's 3? 3. Who's 4? 4, 5. Okay. All right. Charles, once you guys come set up, I was just trying to figure out this problem I gave him. Yeah, you got to figure it out. You will be writing, you'll be doing your write-ups, you're going to type them, you're going to submit them in Canvas. I'll give you the submission link today, later today. You guys want the answer? Yes. How many want the answer? Or you want to wait till lecture?
No.
No.
I know.
You're going to hate me when I tell you this.
Okay.
Or show you. You guys want me to show you? Yes. Drawing it, use 3 straight lines to draw a square. All right, here's the first line. Okay. Here's the second line. Third line.
Oh my God.
What was the assumption you all made? Had to be a shape. Did I say anything about a shape? Never said a shape. Who assumed a shape? I rest my case on being a designer. It's a good lesson to learn. We can turn the lights off. We'll turn off the front light. I will be doing the review verbally. I will provide you guys feedback. You guys definitely should be, I'm encouraging all of you to engage in the discussion of the feedback as well. I will stop the teams But I'll reserve everyone else's right at the end. So when I say this is because it's a learning opportunity right there that I can stop and talk about for learning. So that's the reason why I'll stop you guys in the middle of a slide, for example, to touch on a point because it may apply to all of you. Okay? All right, that being said, it's on you guys.
Ready? Good morning, ladies and gentlemen, and welcome back. Here we introducing you our electric presentation of our robot arm, and this is presented by Arm Coding. Thank you.
Introduce your team.
Here is our robot.
Introduce your team. Introduce your team.
My name is Hao, and
I'm Dan.
I'm Jisco. I'm Anthony.
Maria?
and today we're gonna start with introducing our layout of our electronic chemistry.
So this is pretty much our whole wiring diagram we're going to use for our whole robot. We have every component and every part listed and what wire is connected to where. No, this looks like a lot of wires, but it's not too much. I have another slide. Go ahead with the next one. It's a little easier to read.
Sure. We have labeled out. This is a complete overview of everything, and we're going to the detail of each part.
So this is a little easier on the eyes, easier to understand. So first we have the webcam going to connect to the PC via USB. The Nucleo is going to connect to the PC via USB as well. We have two potentiometers we're going to use, connect to the analog to digital converters in the Nucleo. 4 limit switches, going to connect to digital inputs in the Nucleos. We're going to have 2 power supplies, one to supply 5 volts to a servo, and then the other one that's going to supply 24 volts to 2 stepper motors that have drivers and encoders in them, and then 2 stepper motors that don't, so we're going to have to use drivers for those.
One more quick on the slide. You can show power supply, but we know everything's going to be powered. So you don't necessarily have to have a line to the power supply, just to help clean up the diagram a little bit. That's just going to be a little bit of chartsmanship.
Thank you. And
That's right.
yes, we're going to a little bit more on right now with the motor, and we'll present a couple of videos, which is Maria did a fantastic job. She able to introduce us to something we haven't discovered when doing feedback, which is the Cube ID.
Okay, my part in the project is making, the low-level software, making the motors work, as well the linear switches. This is how I implemented, using the A4980A driver for that step-in motor. So, but before implementing all of that, I had to do 2 things very important before setting everything up. Like, for example, you see right here, this driver has a potentiometer that we need to calibrate to be able to provide the right current to the step-in motor. So, and for that, I used that as a reference, that formula. So I had to go to the data sheet for the step-in motor, see what's the limit current. So multiply by 8, and then right here, they have some resistors that, I think these 2, that resistor that we're not able to see, but that's our resistor sense. So in this case, they were all 100, so it's equivalent to 0.1 ohm. So I multiply that by all of that, and my reference voltage was 0.64, which is the one that I was using, that I had to use for the potentiometer. So for the limit current, the motor that we're using, there is 1 amp, but we had to get only 80% of what the limit is. So once I did that, so another thing that I did is I'm making sure which were paired, to be able to get the coils working. So in this case, red and blue were together, and green and black were together. So once I did that, so I introduced the Nucleo. So I used 2 GPIOs, PA6 and PA5 as the output GPIOs, and then I provide, ground and power to the driver, to turn on the driver, and also this power supply with 12 volts to power the motor. So, and this is the code. This is a test number 1 that I did. It's a very simple, like just showing the revolutions. In this case, is 200 revolutions, 200 steps per revolution. So, and that's what it does. I also did a second test. In this case, I modify, the direction and revolutions to make it work differently and not just like regular. And by the way, I'm using a timer to implement this. So in this case, I do in steps and then like 4 revolutions, and then steps, 8 steps and 4 revolutions. And then I went a little further because I wanted to know how to implement 2 motors at the same time, working at the same time. So basically, I'm using the same diagram, but I just integrate another motor together, similar, the same diagram, same power supply providing the volts, and also I just like jump it from here also to power the other driver. So and I use something. This is implementation that I will see. I see that I had to implement this setup, Crystal Samuel resonator. I had to use 2 timers in this time because it's 2 motors, so 2 timers I have to use. I had to add another GPIO output to the second motor, and I had to set up the prescaler to 71 since the clock is set up to 72. So this is the way I implemented the 3 actos. So I use this feature that the microcontroller has. So then I had to choose this type of 3 actos. So I also had to set up the tasks to be able to provide each task to each motor, and this is how you set it up. So once you set it up, so you can provide a function name and QID generates a function for you. So basically this is the code. So as you can see, I added more pins. I created a micro delay for each of the motors. I created this procedure or module to deal with step in motor 1 and step in motor 2. Right there, I initializing the 2 timers. And right here is where the good part with the 3 actos comes in place. This is you implemented, you work with the scheduler, the kernel scheduler. So, and basically right here, it's like defining the task, and at the same time, we're creating it and executing the task. And right here, where you initialize the scheduler in the RTOS. And this is when you call the functions in the main function. So right here, for instance, instead of use delay, we use OS delay, which is allows to have that delay and just pass, but it doesn't like control the whole CPU. It's just it stops just the task that we're doing, but the CPU is free for other tasks. And this is the view. So it's controlling 2 motors at the same time. So in that way, you put 2 motors, you can actually implement as many motors as you want. Yeah. So, okay, I didn't have time to implement this, but this is something I'm just researching right now. It's about the limited switches. And the information I got is that it has 3 pins. It has these 2 pins. This is the ground, and this is normally open and normally closed. So if you put this together, there is no electrical pad in this too. So this is what I'm gonna be using, because you can also implement the no clothes and ground. You can do that, but for what it is, for our pad, it is more convenient to use this too, because we can use we can start our motor, and then we can stop it until we click the limit switch. So that, and this is basically like a little diagram or flow chart of how I'm gonna test it. Really very simple, just like putting a pin, a pull-up pin for the limited switch, I guess, and then compare it. And if it's low, then I put a Boolean flag that says false, and I'm gonna end the program. And otherwise, if moving is true, then execute the rotation or the steps for the motor, and then just be asking. And that's it.
So let's talk about how we implemented feedback on some of our open loop servers. For clarification, there's a Ouchie Mechatronics login video that we've been using as a reference at this point to fill in knowledge gaps on mechanical components like bearings, and we wanted a tried and true design so that we could avoid some unforeseen logistical issues down the line. But ultimately, our geometry is different. The reason I mention this is simply because I'm pretty sure a lot of people have seen that design, so I don't want there to be any preconceived notions that we're using the geometry that was in that robot, because it would clue you into the solution we ended up opting for based on the internals of our robot. So, two of the steppers that we have already have feedback on them, but the other two are classic open loop EMA 17 steppers, and they have a smaller profile and they're much lighter, which is particularly important for the one that hangs about 7 inches off of the arm. So our solution was quite simple, which we thought was better because it was easier to eliminate some kind of complication, but we were able to design a coupler that could be 3D printed, and it would attach the potentiometer to the GT2 gear that sits at the end. And just to get an idea, this is a British require. How many people are using potentiometers in some form in the Okay, so I mean, as we've been learning in the class, it's a pretty great route to take because it is simple and it's good for a DIY project in this time scale. And some of you might be using the 10-turn ones, which will give you more resolution, but we've placed ours at the end of a 4-to-1 gear ratio, so for simplicity's sake, we are fine with the single turn wiper for a reason I'll actually get into on the next slide. So a single turn wiper has less than 360 degrees of rotation, and upon first glance that does seem like a drawback, because that means that if we are corresponding the movement of the arm to the wiper 1-to-1, then we've lost about 90 degrees of movement. But if you think about the way the arm is laid out, those 90 degrees that we're sacrificing are the ones that the robot would be folding in on itself. So that's not a position that we can't acquire by just changing a different degree of freedom. And so, although it is a trade-off, it's not one that is particularly relevant to our design, and it simplifies it in a way that lets us run with the single turn potentiometer and just have that 1-to-1 correlation, which makes things simpler for us. Hit the next slide. So I just created a GIF here of rotating the arm around 270 degrees just to convey the full range of motion that the arm would have. So I started it in the position, making contact with the limit switch. So at this point, the robot's home, and once it's hit the 0 point, it could move 270 degrees from there. And visibly, it seems like it would cover all of the parts around the robot that would need to be potentially used. And if for some reason those other 90 degrees need to be used, we can always move the robot on a different degree of freedom and get to the same position. So before, with an open loop stepper, the bottleneck would be the reliability of a step. The mechanical integrity of a step is compromised as you go down and you divide your stepper into more pulses per revolution. But if you actually look at the hardware pamphlet that they give you with closed loop drivers, they go all the way to about 40,000 pulses per revolution. On a typical microstrip driver for an open loop, they only go down to about 6,400 because at that point, it all just becomes a blur. But because we're passing it through the potentiometer, we're giving it to an ADC, and on the Nucleo we have a 12-bit ADC, which means that we will have 2 to 12 bits of resolution. But realistically, we're not banking on all 12 bits. There could be some level of noise floor. These potentiometers are not right next to the board. So whether we're relying on 10 bits or 8 bits, there's still quite a bit of resolution to work with, and it'll relatively accurately portray where the arm is in space. And then just to be sure, I made sure that the supply, because the 3.3 volt pin on the Nucleo has a certain current max that it can supply. If we had a 6.6 ohm potentiometer, then it would be an issue, but that's certainly not an issue. You can get those cheap off-the-shelf potentiometers in various different configurations, 100K ohms, 50K ohms. So it doesn't seem to be electrically an issue.
Here we have the gripper, which is we have a little different. We are not using a step motor from this one. We are using a servo, which is controlled by PWM from the Nucleo, and that's why we say kind of different voltage, which is that we say 5 volts. We are testing out if the 5 volts work on the same board, or else we will have additional board that provides a voltage for the servo too. Which is we are able to get this well aligned on our gripper, and we also have the camera installed, which is that we'll be working together very closely. That way, so while the turning, we can. The good thing about the servo is we can use the spike currents as a indicator that we know when we actually grip the stuff, and also we can verify it by using the camera. Which is when you lift it, the block was there, and then when you lift it, if the block is gone, is you grip it, or else you dropped it, and we can back verify that by the gripper currents to check if we really have the gripper in hand. I mean the blocks in hand.
Okay, so I want to talk about the robotic control. So we decided to use Python as the medium to talk and program between us and the ARM itself. Why did we use Python? Me and Dan and I actually have experience coding in Python. It's a lot easier code-wise when you're programming. It has a lot of libraries, and it can also support sensors and vision, which I will talk about in the next couple slides. So our initial plan right now is using the keyboard to control the robot. This is just for our initial testing to see if we can troubleshoot, essentially to see if we can move the arm in the intended way that we want it to go, right? And so that's our initial plan. We're planning on using Beaupre. I'm not sure if I pronounced that right. That is the library used to program your keyboard inputs and connect that to the robot. And then our final intent is actually to use a controller. In this case, we're using Charles' Switch 2 controller. And essentially this diagram here, when the controller will be connected using a serial connection, so it's like USB, into the laptop, to the microcontroller, which will drive the motor drivers, and then obviously control the motors. And the final controls, why we're using controller for the final control for the robot is one, it's last minute troubleshooting. It's a lot easier. You're not really stuck on a computer. We can do more complex testing with it instead of just using keyboard. And for this one, I'm planning to use PyHidapi as the library to program this controller. Next slide. And so this is the camera we're planning to use on the robotic arm. We're planning to use OpenCV and NumPy in tandem. Why we're planning to use that? OpenCV can read the camera in real time. Not only that, it uses real vision, which helps convert the RGB to HSV. So RGB, if you know what that is, red, green, blue, so just color scheme. And HCV is the way that the the library actually converts that data into hue, saturation, and brightness. Not only that, the OpenCV can actually determine the shape of the object based on the contour of it. So that's a big plus. We're also going to use NumPy because essentially you can think of NumPy as like the math, as it says there. It allows us to use, or it uses the calculations based on where the object is between itself and the arm itself to calculate where the robot has to move to grab the object. So that's why we're using both these libraries to essentially control.
We'll actually have the luxury using OpenCV and computer vision to work on objects. There's a couple other tricks that you haven't mentioned if that there are available. We'll talk about that after we come back. So we'll come back, we'll be talking about how to do Python with Copilot Sim and how you can drive your arm. And then after that, we'll be doing, I'll throw a ROS probably in after that, but we'll do the computer vision next, and then we'll probably do a ROS after that. So that's kind of the plan of when we come back, where you guys would be at in software anyways. So that'll give you guys some ideas, but yeah, we will be going over computer vision. And I'll probably over spring break work up the examples in Python. I think all you guys are using Python. Anyone using C#? No. Python, yes? All right, that's what I figured. So yeah, I'll throw together some examples of how that will work even with Copilot. So, FYI.
Thank you for the solid plan. And right here, that's how we connect our camera to the PC, which is we able to locate the blocks. That blocks was cut directly from the Copilot Sim, which is we just did. And then,
I wonder why you guys had that as right here.
that looks very familiar. Yes, and so like that's, well, like the other way, but the other way around, so RGB is actually the basic color. One of the reasons of using HSV is you are able to using that to identify more colors, and which is also spoiler alert. There are a lot of OpenCV is very powerful, and there is actually quite mature. They have a very mature community, which is you are able to get a lot of function out of it. Which is I've been reading a lot about like how Gaussian style how canceling noises, and that was pretty fun. Exactly. Here's the logic basically. That's how I initialize how the camera gonna work, and we are able to achieve that to make that testing.
Let me just go back. If you guys are touched on HSV, I just want to bring it for everybody else for edification purposes. HSV removes the shadow problem. That's really ultimately what happens. So like HSV is going to see that color. There's the three colors that you see right there, so the lighter, the darker. Problems like that tend to go away because a red may not be red if it's the same red, but HSV solves that problem because it removes the components. We'll get into the theory of how that works when we come back.
You just do my mind, okay?
I'm sorry.
That's what you see here. This picture, I intentionally including some other crayons, which is you're able to go. There is a little different from each color, which is like you really need to determine like which color you are really looking for, and which is you can see there. I pick a bright blue. There is a dark blue over there. Some people can say that's purple, but okay, that's not the OpenCV telling me, and which is the red one. They determine that one as the red. That's a red actually, and this is the pink crayon. We say pink now. And why is this like detecting that one instead of this one? Even though the brightness of the center is going in the middle, and because the detail of it is HSV also consider brightness, which is like so if you can see even a shadow here, you will not consider this as two objects. But then there's a little square right here, but that's how they calculate, and it's just spend a moment to actually taking the screenshot. And then thank you for the spoiler. But next one, we will. So after we capture that, we're able to locate what each of the blocks or the objects. Since we have like one complex situation, which is the block with the little Legoland, our king on top of it, that's another powerful thing the OpenCV can do, and which is we haven't implemented that yet, because that we have a complex color, but in event there will be a weird shape, which is OpenCV can also determine from that. Then once we have the location of that, we will use a PySerial, which is we can easily implement that since that's Star Wars Pi, which there must be some connection with Wisdom, yes, they all run by Python. So, okay, you actually can pass over the comments using PySerial to the Nucleo we actually used. Here, pass over. We should connect that using a USB port. One great thing I learned about, again, for the Nucleo, it's actually pretty powerful one than I actually expected. Because that's kind of like the high-end one, which is the old set aside from the old one, which is that's not being, if you want to do some advanced things, you are not stuck with MATLAB. You are stuck with the CubeIDE. Well, which is basically you're able to connect with the SAM port that you writing the data in on the testing board too, which is, if you can see this part gets snapped, that's basically for developer and tester. Even with the SAM board there, you're able to control the board or use the board to control something else. And here is a fundamental idea of ours, which is we have the PC implemented as a brain, we have the Nucleo as a spine, powered by a power source, and we have the arm itself as the shoulder and arm, which actually doing things. The gripper is a head, and also the camera for the eyeball. Well, we have the eyeball in hand, actually. And thank you for that. Thank you for that.
There was one question I was gonna ask, I'm trying to remember what it was, because I think you did answer it. So if I remember what it is, I'll let you guys know, but good. To the rest of you guys out there, you have any questions, comments?
Actually, it's more like a comment. Just make sure you need the enable pin on your motor driver connected to power.
Say again, sorry.
The enable pin on your motor driver, just make sure you connect it to power or ground.
Yeah, don't float it. Yes, right. Yes. Jason?
Oh, should have used enable the legs as your base.
I was planning using a wheelchair. So like we are the wheelchair actually gonna move the road.
It's like for the
Yeah. So
for the game where you actually put eyes.
if you actually see the arrow right there, so like there's like curving arrows, and okay, that's it. And the straight arrow is penetrating into it.
I see. So what's inside the spine, man?
Secret.
Other questions? All right, give me another round of applause. Well done. All right. Oh, you're up. Something different. That's good.
Alright. Hello everyone, we are Skynet. This is going to be our electrical design. My name is Noah Gonzalez.
I'm Nicholas Sanchez.
David Reyes. Max O'Meara.
Send me that one too, I love that one.
Alright, for our design transitions, it's still the same. Generally, we're all just kind of helping each other out, part of working as a team. Before we begin, I would like to mention that the following slides are going to entail working on our improvements on the hardware design, and then it's also going to then proceed into our electrical design, then software design, and then it's going to briefly kind of entail the implementation of PixieCam, and then from there we're going to work on showing you guys a bit of 2 GIFs.
So what we've changed really is mostly just the base. As we had it before, the slide here, we went into here with the metal not letting us rotate as much as we would like. So I went ahead and cut out a little more and then extended the block out so it would be 2 feet. I just added some mounts with ribbon switches that I didn't have and the PixieCam down here.
Alright, so the tower platform, essentially we're going to be using a 1/2-inch plywood to kind of support everything that's going to be that the ARM will be utilizing, other than the power supply. To be fair there, we might include it. But essentially, we will be using we have this sitting over there, but it's going to be like a 3D printed 15 millimeter like volcano type shape. It's going to hold the ball, and we're going to essentially screw that in onto the side of the tower. And so the left side or right side, one of the two sides, is going to hold the ammo, so essentially the balls, and then the other side is going to hold the towers for the blocks. And then the back is just going to hold the Nucleo along with the drivers themselves as well. Now, in the photo here, we show the arc that the tower is going to be moving in. Drew's going to kind of go a little bit more in detail with that, but that is going to include we're implementing that just because we're most likely not going to be including the fourth joint for the rotation of the wrist. That forward there.
And so for the sensors that we have going on right now, it's just mainly limit switches so we can know the full range of motion that we have. And so we could create also a homing sequence so we can count, keep track of how many steps we have to roll it out. And so we have two for each joint, one for max and minimum distance.
Okay, so for the end effector updates, we are adding our about 4 millimeter padding faces of the jaws, which fully then encloses the end effector and reduces our maximum opening to about 39 millimeters. And as per the suggestion, we are giving the positioning of the servo via the potentiometer wiper. So we've made that adjustment, and we're going to do testing for that.
Have you guys opened up and soldered the wire on you?
Yeah.
And you guys put it all back together?
Yeah, we did that yesterday.
That's like surgery, isn't it?
Yeah. And we did decide against having the rotation for the end effector just due to reconfiguration and time constraints. So the end effector will place the blocks following the arms apart.
So the holders on the actual stand will be set in a certain way, so when we have our initial one, they'll know exactly where it's at, so just pick it up without necessarily using the fixing cam to identify it.
Are you guys using fixing cam?
We're gonna be using it for the attack portion.
Okay.
So we have the electrical design. We're running the motors off of 24 volts. Currently, the servo motor is going to be powered separately because of it's between 4 and 6 volts for max voltage. All the signal inputs are coming from the Nucleo, and the Pixie Cam will also be powered separately and be connected through the Raspberry Pi straight to the laptop afterwards.
So for the electrical design, essentially this portion here will be utilizing the 3 drivers in series. They'll have their own separate connections. It's just to kind of simplify the wiring so it's not like all jumbled for you guys to see. It's kind of generalized, well, simplified. Like here we'll be utilizing the pole in the direction. That's going to be where the Nucleo. And so that's, and then we're also going to have the motor coders. We have it all wired up already, so it's verified on that. But yeah, and then we're also going to be using the bipolar.
So we have the servo motor connected separately, powered by essentially it's going to be either through a laptop connection or a separate 5 volt. We do have a monitor, but this is for the Pi output.
Yeah, so pretty much we're utilizing the monitor to view the Pi desktop.
We're going to be utilizing the limit switches to get the max range, which is going to be going through the Nucleo to get the signals.
And yeah, so that's going to be utilizing, as we mentioned, the cathode cable.
Yeah.
So we've soldered it to where all the positive and ground are all together, and essentially it's going to read the high low. And then for the Raspberry Pi, kind of like Max mentioned, essentially we're going to be using a dongle. Well, let me start from the top there. So the HDMI is essentially to view the desktop for the Raspberry Pi. And so that'll display the coordinates of the block or whatever we're trying to view. Then the USB dongle is going to send the coordinates from the Raspberry Pi, from the PixieCam to the Raspberry Pi. And that'll take in also Bluetooth because Bluetooth dongle for like mouse and keyboard. So we can kind of operate the desktop of the Pi. And then that'll also need a power, like a Type-C from like the wall to the dongle itself, because when we try to power it on without that power supply, it kind of wouldn't drive the PixieCam. And from there, we would use a micro USB to connect from the Pi to the laptop. We haven't tested that out just yet, but if it can't extract the coordinates, then we will most likely be utilizing a Ethernet for that.
Okay, and then this is just the initial layout for the software. We have acquisition, communication, and actuation. So for the acquisition, essentially we're going to be getting the coordinates from our PixieCam 2. This is largely going to be used for the attack portion. That way we can do it all automatic. So we can find where exactly the block that we need to attack at, so we can get the direction that we need to place it. While setting up the blocks is going to be already essentially coded in, hard scripted, so that we could have the preset where the blocks are, put them in directly, don't necessarily have to worry about that. So we're currently using Linux to interact with the Pi for the PixieCam. We're using Python script. Should be good. And then for the communication, so we're going to be going from the Raspberry Pi to the PC to the Nucleo. So we're going to be essentially, yeah, so once we get those coordinates, we're able to send it to Capella Sim. We're going to be using Python as the main script. That way we can figure out the inverse kinematics to find out exactly how to move our robot. And then once we get those joint angles, it's going to be sent to our Nucleo, which is going to then update the Cube IDE, which has the initial program, so then we know exactly how to, so we get the robot going, interact with the separate motors. Yep, so this is for the actual actuation. Like I said, we're using Cube IDE for the with C++. The interrupter is, like I said, once we have the joint angles from the Capella Sim, go directly to our Nucleo. We'll set up our step generation, so we'll get the required steps needed to get into that angle for our robots. And then essentially we have encoders on the back of our motors, so we can get using that for our feedback.
Now, this was the PixieCam implementation of it. We used the Piximon, and so essentially, what we would have to do is set the signature to be whatever color. So when you click the set signature, it kind of freezes the screen for the Pixie, and so you can choose whatever color you'd like to assign to that signature. I just had a Neutrogena while I was there. And so what that does is then you can, after highlighting that, you would set that as a signature label, and you can name it whatever you'd like. In this case, I chose blue. In the case that, like how Charles was kind of explaining with multiple colors, we can use the CC set option, and that kind of, you can choose two colors in that. I guess, let's say for instance this bottle here, you can choose it to where the black and the blue are kind of one object. And so you can kind of use that for the shadow.
Does PixieCam also it does shape recognition as well, right?
Yeah, it does. This was just a test script that we found on the GitHub.
Mm-hmm.
Yeah, so that was just extracting a test.
Just kind of give a mess with PixieCam and do a general idea.
Yeah, at first, as I mentioned, with the whole power to the dongle, we were getting a connection to the PixieCam failure, and so once that was connected, it was successful. And so when it detected that, before I get ahead of myself here, the top portion is just kind of implementing the libraries for that implementation of that GitHub. But yeah, once we were able to detect or test out the Pixel Cam, it was able to provide to us the XY coordinates along with a few of the other, like the width, the height, age, general information.
So this is a little bit of an overview of the CubeMX software that we use to set up all our pins. You can't really see them, but we just have you can click on the gray ones and then it lets you set it to a timer, GPIO, input or output. This is more or less an overview of all the pins. We have the limit switch pins. These are set as an external in the remote so that when the switch is hit, it automatically it immediately stops the motor. It doesn't wait for the code execution. And you can also see you have the 3 direction pins, the 3 enable pins, and then around here the timer pins are for like the encoders and for the post. And the direction and enable pins are just regular GPIO. We just need them for the drivers to set the direction when to turn on the motor. This is our timer setup. This is for the PWM here. 2 of them are 16-bit timers for 2 of the motors, and then for the lead screw, since it would rotate a lot more, we did need 1. So it's not here, but we did find a 32-bit timer so we could keep track of all the steps in the full range. Oh, and also, sorry, I added a prescaler because when we didn't have no prescaler, our PWM was like around 60,000 hertz, and it would just like make the motor whine. So once we dropped it to 83, it drops our frequency to about 700. But for the lead screw, I did drop that again to about 60, so it could just spin a little faster.
Yeah, so that was just a simulation that we implemented last time. And then that was the part moving. And then we have the joints kind of just moving 2 at a time, just because David was testing out last night. The motors, and it was because of the power supply was drawing too much, so we're going to test it out with all 3 with a proper power supply. It should work.
And then just a quick rundown on the parts list since we didn't quite get to it last time. We obviously have our 2-step motors for rotation of the tower and the translation of the carriage, and then our other step motor for the rise tower. We obviously have our power supply. We have our wires for extended connections, the belt deploy system for the carriage. All of our parts are printed out of PETG. The servo for the end effector, and then the bearings and rods as well. And then our 3 digital stepper drivers for our motors. And then this is the original schedule, and we've been able to stick to it. So.
Good job.
I don't really have any questions. Well, presentation, both presentations so far.
Okay. But from the audience, questions, comments? How'd you do that kind of questions, maybe?
You guys are showing your step and motor drivers. You said they were connected in series, but you shouldn't be connected in parallel.
Oh, so yeah, sorry, I misspoke about that. Yes, I do understand what you're saying. Thanks.
One question. So I'll just give some knowledge from you. So you mentioned like using like Linux, Python and Linux. Do you mean by and Linux is operating system? Oh, just the Raspberry Pi.
Yes, yeah. So we're utilizing.
Okay. And by using Python, you mean like you pre-write the code? Pre-write the comments in there.
Yes, yeah. So we'll be extracting the coordinates from the Pi and utilizing Python to kind of communicate.
Thank you. I'm gonna ask you later what the
Consulting fees, all that stuff.
Yeah.
Okay. Yeah. One problem I have is like I try to use my PC because I have Linux installed. I guess it's operating VM, kind of like VM 2.0. But I try to use that to control it won't read the camera and the nuclear at the same time. And it's probably because I'm using Windows operating system, so I'll figure it out.
Okay. It's more of a question for you both, because I think the last group, they have their camera connected directly to their laptop. what would be the advantage over using the Pi, like having the camera connected?
Well,
to the
it's a slightly different, I think Noah's can have the answer on this as well, but they're using the PixieCam.
Yeah.
So PixieCam actually works better with the Raspberry Pi, I think, than the PC. It does work with the PC, but I think historically you've had more success. I think that's been, other students in the past have also found it works better with the Pi. It doesn't have to be, but they kind of go hand in hand better.
Gotcha.
So really, I think what you're looking at is the Raspberry Pi and the PixieCam as a smart vision sensor as a package.
Exactly.
And that's how you guys are looking at it as well.
Yes, yes.
As an easier way to describe it. So it's like a custom, we can customize parts of it, but you're using the smarts of the PixieCam itself to instead, like Charles is doing OpenCV, that's the other solution. So it mitigates the OpenCV code if that's not something you want to focus on. Anyone else? Those are good questions.
Yes, so, so are you going to use the PC and the Raspberry Pi together, or just were you like on the demo on the competition day?
Yeah.
Are you going to use the PC in parallel with the Raspberry Pi?
Most likely, yeah. Just because it will have to kind of extract the coordinates as live as it goes to kind of be able to place the ramp to wherever we want the shot to be shot.
Yeah, so don't forget, there's two specific, and there's a possibility of a third that I need to get the leads, get their opinions on. You guys can talk about it. There's potentially the autonomous, if everyone's going to be autonomous. There's going to be the teleop, and then there's going to be the remote op. So the teleop means you have to use a camera of some kind mounted somewhere where you're using that to drive the robot. Remote is, I'm looking at it, I'm actually just maneuvering it directly that way. Jason, a question?
Can you guys remind me how you're moving the data from the camera into your overall?
The laptop?
Yeah.
So we'll essentially, we haven't tested that out exactly, but we're going to be utilizing a micro USB. If not, then we'll most likely just be extracting using the Ethernet port. From the dongle itself.
So like the data you get from the camera, how does that like go into your mathematics or like your parameters and stuff? Do you have like an idea of that?
We're still working out exactly how to get it to speak with the Capella system. So we need to be able to essentially put it in a file so that draw it into using that different script, so then we can get whatever those signals are, so that we can also convert it to what we need it to be, and then we can send it back out, reconvert it, send it back out to the Pixio to get what we need.
And in fact, you guys are
We're really working on it.
You guys are highlighting something you guys should be working on right now. Most of you have multiple processors. How do your processors communicate with one another? You're all talking about using Pi serial. Have you guys written your protocol yet so that this device knows how this device is talking? Yeah, you're going to send serial, but what are you sending? What is the information being sent, and how is that information being structured and then extracted on the receiving end, and vice versa? So that, I think a lot of you are going to be working on now.
Yes.
And that's really very customized. There's no specific way. ROS can start to solve that problem, but not really, because you get into ROS, the serial communication, the ROS has to then live on the embedded controller. Then you talked about micro ROS, and it's a rabbit hole to go down. So it's really not a good answer necessarily unless you already know it. So keep the serial communication easy is my suggestion. Sending across fixed width data where you have this byte means this byte means this, and you send across 10 bytes and you call it a day. And it just really, that's my suggestion for right now for all of you guys, keeping things very simple, get it done. And that's probably the best approach I would suggest for all of you. Other questions? Give another Yeah, some of the plastic clan pictures also. We'll use them liberally next year. Oh, by the way, leads, please send me the presentations. Send me the presentations. All right, group 3. I think it's Will, right? Are you guys learning something by listening to the other teams? That's the objective. A lot of ways to do this design. So, real quick, as Williams is setting up, I'm thinking, do you guys want to do the competition in the morning or in the evening?
I think it depends on the day, because if we decide we want to do Friday, like the week before,
We could do Friday evening. Might be less stress and more fun.
Oh, I
Have
have
pizza.
lab. I have lab.
Do you have lab Friday night?
Yes, professor.
Why?
From 7 to 10. That's
Why?
because
We'll talk about it later. How about that? So we don't necessarily even have to do. We have to make sure the lab, this room is open. Obviously, it's open on Monday or Wednesday mornings. But again, is this something we can talk about? We also have graduation to contend with as well. So graduation, I think, is on Thursday. Is that right? That's Friday. So we can't do Friday finals week because we have graduation.
So you guys have Friday? Ours is Saturday.
No, we're all the same day. Engineering's the same day. I don't know what day it is. It rotates. Every year it changes. It used to always be the same day, and all the other colleges saying, well, why does engineering get the best time? Because we're the best college.
It's
But
8 in the morning.
so they're rotating everybody now. So I never know what day it is anymore. So, all right, that being said, we'll figure out what day we're going to do. If we can do it in the morning, we can do it in the evenings. And by the way, I'm also going to I started talking to some educators, not necessarily college educators, good friends of mine who actually teach engineering. And they're going to be reviewing, they're excited to review your report. So again, don't forget, the day of the competition, you have the proving grounds to make sure you can do everything. And also you're seated by your report, which means the report has to go to the reviewers ahead of time. I will grade the report, but they will seed based on the reports. So it's a twofold thing, right? So they're going to give a score on how they think, and I give them a rubric, and they're going to give you a score on how they think you did. And then from that, in combination with the proving grounds, that's how you start who's going to be playing against whom. So who gets the bye, because we have 5 teams. So 1 gets the bye, 2 plays 5, and 3 plays 4. And higher seed gets the choice of what side they want. I mean, so that's really what it comes down to. Any questions on that? Cool. All right, one. Yep.
Hello, my name is William. My name is Thomas. John.
Robert. And then I will. So before we move on, I just wanted to give kind of a rough overview of kind of what our design looks like. So here we have a picture of it, and then kind of how the electrical components fit onto this model that we have here. So on this backside, you can't really see it, but this is where our motor driver is going to, or our motor, excuse me, is going to be for our rotation. Up here, this right here is our horizontal motion, and then down in this box down here, we have our vertical motion. And then connected next to each of these motors is going to be a potentiometer to measure our positional feedback.
Just kind of an overview for our electric stuff, how much has changed. We're going to be running an Arduino Mega and an Arduino Uno. The Mega is what we're going to use to drive our 3 stepper motors in parallel. And then the drivers we're using for those are the A4988s. And then the potentiometer, as you mentioned earlier, we're just catching that for rotation motion. And then we're measuring the voltage difference across A to E. And then we just got 10 potentiometers just because we wanted a higher resolution, and just to simplify our lives. And then the Arduino Uno is what we're using on the arm itself to change orientation. And then those are 3-pin servos, so we're just using the parallel potentiometer to track position.
So you guys are tapping the inside of the potentiometer as well. Have you guys opened it up and tapped them yet?
I have done it for one, but I haven't used one reason for that part.
So you've done it before now for this class?
Okay. And then the way we're connecting the 2 Arduino boards to is over serial ports to the PC. So then we're communicating with Pi Serial with Compelling Set. And then basically general overview for that.
So this is the overview of our stepper motor connections. As we said in the mechanical presentation, we're using NEMA 17 motors, and we're connecting them to, as previous group mentioned, 84980 drivers. Also connected into 10 potentiometers, like Will said, for better precision. And it's all going to be connected in parallel alongside the Arduino Mega board, primarily just to keep the general voltage down because they are kind of high voltage for our power supply at least. And then also attached for the same reason a voltage regulator. And yeah, the Arduino board itself will be connected to a PC in order to power it and of course run the respective codes.
And then here we have our servo connection to our Uno R3. It is connected to our PC via the port that's already on there. We have our voltage regulator so that we have the correct voltage from our power supply being our 5 volts so that we don't burn out our servos.
Real quick on that one, I know this isn't probably, you don't have a lot of experience in this area. You're gonna drop 12 volts down to 5 volts with 15 amps? Is that what your draw, what's your draw gonna be?
Servos draw the maximum
1 amp, so it's gonna be 3 amps. So that 3-terminal regulator, that LDO is probably what, 7805? Be careful, I mean, the 15 amps that you're supplying isn't really a big deal, but you're gonna be dropping 7 volts at 3 amps, so it's gonna be 21 watts. That 3-terminal regulator is not gonna dissipate 21 watts. So, you can just be careful, you might just wanna maybe use a plug-in 5 volt, like a wall board, that does 5 amps and call it a day. That might be an easier solution instead of trying to mess around. I mean, power supplies are relatively trivial, but you're gonna have to worry about that delta V times your current, that's your heat dissipation. Because that's just gonna go off in heat. So, it's not a switcher that you're showing on there. You're, no, take that back. You're using an LDO, right? Yeah. Yeah, think about using an alternative approach on that. That's just be my suggestion. I don't know.
Yeah, and then for our stepper code, as you mentioned earlier on the 84988s, we have the step and direction pins. Basically, just define those and use the steps per revolution that you see in the data sheet. And then this is kind of just boilerplate code just to run you through revolutions 1 megahertz. Yeah, they're parallel. We just had it set up so that it does one at a time and then all simultaneously.
So that was the other question I was going to ask on that. That's on the stepper motors. Your power supply, is it rated for one motor at a time, or is it going to be rated for multiple motors simultaneously?
It's rated so that it can run all of them simultaneously, but we're trying to run them one at a time.
Okay.
Don't worry about it.
Dude, you don't have to be as fancy as Maria doing the free art talks with it. She's reading the comments.
And then with respect to the servo motors, similar to the stepper motors, but we're going to define it this time using the built-in library in our Arduino IDE code. And of course define what pins they go to. And unlike these stepper motors, they're going to be connected to the analog positions on the Arduino Uno board. So we're probably going to have to hard code the position as opposed to the stepper motors.
And then this is our code for measuring the actual position with our potentiometers. This is only one section, so this right here is actually only just our rotational angle, but the structure is just about the same for the rest of them, just with a different equation here for our translation from our voltage and how it relates to our height or our angle.
And this is our Copelia model. So right now I'm just trying to get some basic IK working, so I have the little dummies made and stuff. Still doesn't work.
I can't remember if I posted the.
I have no clue.
I'll post it for you guys. We're going to be. Okay, yeah. Remind me if I don't post it to post it, but I'll give it to you guys for sure. Okay.
Yeah, so we have the Revolut joint in the base, all super prismatics, and it's going.
It's pretty much what we have. It's kind of.
Oh, you put the explode video?
Well, I didn't. It's
doing that number. But then I.
So you have to worry about
I just
respondability.
Yeah, that's exactly what I was about to get to. And you have to like alternate the layers.
Yes.
So then.
Yep, exactly. Got it?
This is a kind of rough overview with our PySerial code. This one is going to be PySerial and Coppelia Sim converting it to a Node API. And all honesty, at least I am kind of very new at this, so it's really rough.
Okay. Gets the job done on that. So this is obviously so you have an Arduino, two Arduinos talking onto the PC?
Correct, yes.
Each one has their own COM port, so that's the easy part, 3 and 4 on there, okay. Yeah, okay, so so this is the Python code, this is your Arduino code, or this is your Python, this is your Python, isn't it? Yeah, okay.
Yeah, just
I'm
put it in
talking out loud.
Arduino for presentations.
Okay, yeah, so I'll show you guys, like when we come back, how to talk to the remote API in Python, as well as then however your interface talks to the serial port.
And then the kind of continuation, the code we're going to implement into the actual Arduino boards. Again, pretty rough. The plan is right now it's subject to change.
Sure.
To essentially send dummy sensors or the data from those dummy sensors, and hopefully by doing that we can transmit that data into the simulation, and of course get proper communication between Coppelia and the Arduino boards as well as the.
So I'm going to jump here real quick and Thomas. So like I was saying before, having the communication that you kind of, this highlights it, if I want to bring it up, is when you're sending the data between it, the protocol, keep it simple. I don't know if you guys are just doing fixed links, but like I said, allocate like say 20 bytes or a 20 character string and send the data positionally. You don't even have to say like what you're doing inside of it, just every byte and just extract that byte. That's really one of the easiest ways to do it. Just if you want to just understand that. So, sorry, if you want to jump in because you're kind of showing that right now.
And finally, it's again rough script of the Coppelia script that we may use, and it's more so an overview on what data it's going to pull from, whether it be the Arduino Mega board or the Arduino Uno board.
So are you saying, so your Python, are you talking to Coppelia via your Python, or are you doing this internal to Coppelia? Because what I'll show you guys when we come back is how you do that external API, like you're talking about, in Python, how that talks to Coppelia.
Oh, like a separate part of my chip talking.
Right, so instead of actually running the Lua script like you guys were doing on the simulation, you can literally follow that same approach, but do that in Python on the PC. And then you don't have to have it doesn't, you don't have to look at the Coppelia script. It lives all on that Python script instead. So it's talking to this on the PySerial, it's talking to Coppelia also, which is a little bit more organized from, and I don't know if the Lua actually would go out and talk to the external world over that. And supposedly it does, I've never tried it yet though. So.
Because they talk about like Lua socket and then a bunch of other.
Yeah, so that's stuff we'll go over when we come back. And I think it'll make a lot more sense. Since you'll all be about at that point, I think. Hopefully.
And I think that's about it.
Good. All right, so questions from the audience again? Charles is.
I'm sorry, I tried to follow regularly, but I couldn't. How do you want to get, like, what kind of data you're getting from the, it says like measuring the potentiometer, and then you are measuring that from the Arduino? Or?
Yeah, we're using analog tape to measure that wiper voltage, and then we're just sort of using that as a way to approximate like the rotation within the separate motor.
And you're doing a subtracting? So we're subtracting,
like target position versus like the one
that's
that
correct. Okay. I think, no, that's not. I'm asking it.
So if you guys are still going to use that voltage regulator, I would suggest you're getting an heatsink for it because it'll get really hot.
That's right, so not use a regulator. Yeah, just use this 5 volt, right? This 5 volt power supply, USB 5 volt, you know. You cut the end off, get the voltage, call it a day, right?
What kind of
sensor you guys using?
We're using just those 10 counters. Those are the only sensors we're using for like position feedback.
For your camera, did you have a camera in there?
Not yet.
So your teleop might just really put a webcam on there and drive it from a webcam and not do autonomous? Okay.
At this point.
Autonomous was a stretch goal, but if people are doing it, they're gonna get bonus points for that, for sure. I think Charles, you're still on the, I don't know if Jason or you guys are on it, but, okay, is that it? Are we good? Any other questions?
What was your team name?
What did you say?
What was your team name, sorry?
Stay.
Spanish.
All right, give a round of applause again. Let's go. So, as we're waiting for Jason to come up, how many are going to throw that little question I gave you guys at the beginning of class to somebody? Make a square using 3 lines.
I could, but I like the fact that there was like an actual lesson behind it about like assuming. But like no one in my family is an engineer.
It doesn't matter. So it's a fun little question. All right. You're up.
All right. I'm Jason. I'm Cornelius. I'm Ritu.
I'm Angel.
I'm Anthony. And we are Plinka. So here's our overview. We'll start off talking about our mechanical review, then move over to electrical, and then end on software.
So this is our finalized mechanical design. For this one, we have our simulation picture. And on the right side, it's our reference to Post 3D.
This is the Coppelia design. This is our Coppelia model, but our actual design is very different.
So we decided to do a new base since we're using a wave drive. It's going to be in here. And then we have a stepper motor under it. We're also adding 4 potentiometers. And we decided to put pulleys on the bottom.
We're also using different gear ratios that are going to be around 18 to 1 on the first lane, and then maybe 3 to 1 on the other.
So real quick, I'm stop here. Did you get the wave drive in yet? Oh, you were prepared. I love it.
Share.
Okay, I don't want to steal your thunder.
Okay. No, actually, it's too small.
Okay.
Just for you to see it.
Okay. All right.
It took a while to see it come, but it came in yesterday. Nice. Do you have anything else to add to this? So we're using potentiometers. We're actually going to design some gears, 20 to 1 gears. So we'll add a gear here, and then as this turns, there's going to be like another gear on top, and as this turns, it'll turn the gear and turn the potentiometer, and that'll we'll read it off using a wire all the way back to the base where we're going to put our Nucleo there. Just plug it into our Nucleo. So that, I just wanted to explain briefly the wave drive. We went with the 1 phase. So that's just how it works. It's not that bad to understand. So this is a bearing, and then as it rolls, there's gonna be balls here, and the balls are against the bearing, and there was a wave disc, which is like a wavy thing. So it'll turn, and 20 to 1. Yep, it's just a gearbox.
Is this the deformation?
That's for the that's the cage that holds the balls. So
Where's the deformation?
It's going to be a bearing. This is the deformation.
So, okay. So I think really what you have more is a cycloidal.
Yes, it's more cycloidal.
Because a wave is like, this is different. That's where I got really, really nervous.
Okay.
So, yes, you want to help finish, you guys, if you don't mind? So there's different kind of gear trains. You guys have all seen the mesh gears. That's what all doing. You got the pulleys. I'm going to steal your thunder and just explain real quick. They all have a little bit of backlash, especially when you start to get high gear reductions. Now, another way to do gear reduction is a worm drive. Worm drives have a lot of backlash. So you hold one side, the other side's going to pivot a whole bunch. But you get a really great gear reduction. And it's not back drivable. What I mean by back drivable is your load can't drive your motor. Gear trains like the spur gears and the cascaded gears, those oftentimes can be back driven, which is not always desirable. So the worm gear is non-back drivable, it has a lot of slop in it. Now we go to more advanced gearing assemblies, we have these things called wave drives and cycloidal drives. And so really what this thing is really more cycloidal. And what happens is, think of it as it engages and grabs, and then engages and grabs like this. So the way these pins and balls engage one another is how it drives. As opposed to the gears, which are always meshed. Aside from the wave drive actually uses the deforming ring as the way it grabs and moves and grabs and moves. And there's an eccentricity disk in here. Where's your eccentricity? This is your eccentricity?
Yes.
Yeah. So the way there's this little bit of an eccentricity, and it kind of goes around and it grabs, and as it goes around and engages, that's giving the gear reduction. They're very fascinating. I mean, it's definitely a rabbit hole you can go down. It's a lot of fun. They're really, really cool. I don't have as much worry anymore because you're not doing an actual wave, but you're doing a cycloidal. Cycloidals are doable. When you said wave drive before, I got really, really, really nervous. But they have to be smooth, otherwise they can catch. So actually, I have one in my office I could have brought you guys. I didn't know you actually use cycloidals. But for those interested, let me know. But this is really cool. This makes me feel better.
Okay.
So yeah.
That's good.
All right.
So just as a review, this is the DH parameters, but we're not actually using DH parameters. We're using Jacobian. So yeah.
Which, by the way,
they arrive at the same answer, but
yes.
It skips some step. That they both, yeah.
You need the DH parameters to get to the Jacobian.
Yes.
Because we have to. That's what we talked about in class today. So we're going to go through the S matrix. The S matrix is derived from the T matrix, from the R matrix, and that will give you the Jacobian. You haven't learned it yet, but that's what we will be doing in detail. And that's going to be the bonus. You guys do the bonus on this, and you show that the Jacobians with the simulation and the math agrees with the theory. That's the bonus points. So, go ahead. Apologize.
So this is our basically the whole overview of the circuit design that we're going to be using for our robot arm. We're going to be presenting each section more thoroughly in the later slides, but as a brief overview, these will be our NEMA 17 motors over here connected to the motor drivers. It's going to be all about the motor drivers are going to be powered by the 24-volt rail. We will be using electrolytic capacitors to reduce any noise, make sure there's no current spikes or anything like that. And then from here, the inputs, step inputs, and then directional inputs from these are going to be fed to the nucleo. And then from here, we're going to be also utilizing a servo motor. So, so we're actually using a separate power supply for that because 24 volts is too high for that, so we didn't want to burn it out. So that's going to be fed. And PWM signal for that. And for our buttons, we're actually going to be using for actually move the joint.
Oh, it's like a user interface?
Yeah, basically.
Okay.
And then for potentiometers for basically the position is that's what we're gonna be position feedback to the nucleo. And then for our
yeah, for you to remember, stop real quick. So you use the buttons for the user interface to move it. How do you go forward and reverse? Because right now you just have a go, no go.
We're actually this is like a left.
Okay.
Addition.
We'll explain it on the later slide.
Perfect. Okay.
And then for our servo grip, we're actually going to be attaching our pressure sensors. That's going to be oriented in the voltage divider configuration. And then so for the pressure sensors, they're going to be able to sense any interference for the end. And then so the moment it tension on the end, it's going to be able to stop the motor and be able to figure it out.
Did you guys already buy those pressure sensors?
Yeah, we got them.
How do they? Have you tested them?
I've tested them. They work.
Cool. Awesome.
Then we're going to be using MATLAB Simulink for Nucleo to be able to programming. Okay.
So we, as mentioned earlier, we do have two different power supplies. So the first one we're using is a 24 volt, 20 amp power supply. So this is the power supply we're going to be using to drive the stepper motors, right? So one thing to note also is that this is going to be where all the grounds are kind of tied together, so that way there's no issues with grounding. Yeah, there's just terminals. One kind of funny thing was that we had to actually strip a 14 gauge wire to connect it. So that was kind of fun. But apart from that, yeah. There was also for the wires that are directly connected to this power supply specifically, we were planning to use a bit of a thicker gauge wire so that way we don't have to worry too much about.
You're talking about the motors or to the plug in the?
So from the power supply to whatever it's connected. So in this case, it would be connected to the stepper driver.
Okay.
So we just want to make sure that it doesn't burn up, right?
Yeah, you can probably get away with 18 stranded.
Yeah, because we're using 20 right now.
Yeah, that's a little small for that kind of current.
But what we're planning to do is so there's like actually there's like 3 terminals here that are positive voltage and negative.
Right.
They're all technically from the same point.
Correct.
But what we're gonna do is we're gonna have like 2 different wires. Like we're basically splitting it up, so it's not just one to one. Yeah. Yeah, that's about it for the 20-foot volt. Wait, and then you wanna do the 6-volt.
Oh, yeah.
Yeah.
So for our 6-volt, this will be used for our servo motor. And we're actually going to be connecting this to an outlet to get it like actually powered on. Right here.
And then you're also powering the Nucleo. That just comes from the USB on the PC.
Yeah, it's straight USB.
Okay, so for the stepper motor drivers, so we're using 4 E-Series NEMA 17 stepper motors. We just use this one because it's pretty popular. There's a lot of documentation, so it's not as hard to like troubleshoot, right?
Every 3D printer is using them, right?
Yeah, pretty much. Yeah, and this is our this is basically what the wiring diagram for the stepper drivers, right? So over here we have all the connections for the microcontroller. So reset and sleep are going to be shorted together. So you know how like the Nucleos have like those jumper, yeah. I just don't want to do that, so it's easy. Step here, that's for your PWM signal. And direction here, you either tie it to high voltage or not high voltage, plus to VDD or ground. So that'll determine what direction the motor turns. And then this is just for the VDD and ground for the board itself. This is where the motor itself actually gets connected. One kind of interesting thing that happened with our motors is that it was wired in the wrong way. So we had to like open up the DuPont cranks, pull it out, and then wire it manually. So in the later pictures, you'll see it, and you might see it, but you'll literally see like the wire just kind of like sticking out like that without the DuPonts. But yeah, we did rearrange it and we did confirm it actually goes spin. Yeah, and then this is where our motor power goes to, these 2 pins, the motor and the ground. And yeah, we do have the 100 microfarad capacitors to protect against voltage spikes and current spikes.
So real quick, excuse me. Most of you guys say you're using the 4980H, is that true? Here's my suggestion. They tend to burn out when you least want them to. Exactly. Have spares. I cannot stress that enough. Every year, Dr. Boscovich, my motor driver burned out. Buy extras. Even if you don't need them, maybe another team will. If every team buys extras, then you can sell them or do whatever you want to do to them. But in the spirit of competition, we don't want to see a robot stall out because the motor driver burned out for whatever reason. But they are notorious for burning out the day of the competition. So have spares. I would have like a 1-to-1 spare. So 100% spare. So if you're using 5, buy 10.
That's good. We got 10.
And maybe more. Maybe 15 is not a bad answer. So amongst all of you guys have it up. So that's just lessons learned, but because they're very popular, they're very easy to use, as you're saying. But yeah, okay. Go ahead.
So for servo motor, so we're going to be working the wire. It's going to be powered by 6 volts. Then straight to the Nucleo. Use the power to provide the PWM signal. And it's going to be connected to like the regular capacitors to like regulating current spikes and all that.
Okay, so for the two sensors that we have, so we do have the 10 turn potentiometers for joint position and angle. And just for completion's sake, the turns you can get you can figure out the position from getting the voltage and then using a voltage divider. You just find what the voltage is on the wiper. So one of the pins is connected to 3.3 volts, the other one is connected to ground, and then the wiper itself is going to be connected to one of the analog input pins, four of them, right? And each of them are 50k ohm potentiometers. Additionally, so this is the one that's kind of different from a lot of other groups. We have what's called a force sensitive resistor, and what it is essentially it's a very thin film that if you place it on a flat surface and you press it down harder, the resistance changes. So normally this thing is normally like open, but as you press harder down, it increases. It decreases in resistance. So this is a lot closer to what how we're gonna wire up this sensor. So you have the 3.3 volts. This is going to be the gripper, the force sensitive resistor. And yeah, no polarity. So you just connect one side to VCC, the other one to this joint here, and we have another resistor here that's connected to ground. And in this joint, it's going to be connected to the analog inputs. Then yeah, right now we're planning to we're only planning to use one, but you can technically use two, so that way you can make sure that there's even torque being applied to both sides. But technically you can get away with one. Sure. Yeah.
I think you might want to do two instead of
Yeah.
And so you only go between 1.5 volts, 0 to 1.5.
Yeah. Tara will mention, just to remind that this is back to feedbacks and controls. This is our P and our PID. So yeah.
And so this is how we're actually controlling our robot arm. Two of them are going to be assigned to actually move it in a certain direction, and two of them are actually going to be control the joints. And we're meant to actually open and close the servo motor arm, and then there are other techniques to visual output on the video to actually power the
one thing to note, I know this looks impressive. This isn't exactly what we're using. We're just only using the button. But this is basically what the buttons look like. They're pretty nice, big. But yeah, as he said, we're gonna use two buttons to toggle between which joints. So it's like if you go from joint 1, you go to joint 2, joint 3, or if you want to go press the other one to go back 1.
So you're not running ESP32s in the background?
No.
Okay.
Yeah. And then we have two buttons. So ideally, this would just move one direction, this one moves the other, and this just toggles the gripper. And this is going to be the nerve center of our project, of our robot arm. So it's connected to. So the reason why we chose this board, the Nucleo F767ZI. Well, number one, most of us already had experience with it last semester. Number two, plenty of input-output, so it's going to be easy to work with, and especially since we do need 6 analog input pins and 13 digital pins, and they're all connected to all those components over there, and so.
You're going to click the whole thing soon, like that? It'll do it. It's going to be tricky. You may need to use Stateflow, because to try to sequence the Simulink, it may be more challenging. Where in C you actually do cases and vowels, you don't really have that in Simulink. So Stateflow might be your friend. So I'm just going to FYI that for you. So you have different stations that have different behaviors.
These are just some pictures. If you see here, right, you see how there's a DuPont here, and then over here it's just kind of silver. That's what we meant when we had to take out the DuPont crimps. But yeah, we did verify it did work, because earlier before, when we just left it at the default configuration, it just kind of jittered and then it just stopped moving. Yeah, but after we did that, after we rewired it properly, it started moving properly. Yeah.
So here is a video of our robotic arm in Patelia. It's moving at
through the use of pH parameters. This is just the first step in just trying to pick up a blocks and then moving it at a designated position. The meshes are still raw. They're subject to change.
Gets your job done.
Yeah.
So, I wouldn't go crazy on making the gingerbread look good.
Yeah.
In that sense, get the functionality working first. The gingerbread's just gingerbread. The other one we're gonna say gingerbread, right? Yeah, it's just the decoration.
So here's our overall block. This is the diagram of our entire robot. All of our hardware with the sensors, motor drivers, the controller being buttons, power supply being supplied to the hardware. 3 outputs coming from the hardware into our Nucleo. It's generally into an ADC. Then it's connected to one of our PCs, which has Simulink and Capella running at the same time. It would first go through MATLAB, which would then convert the data from the Nucleo to a Python script. There's also a mention of 0NQ, which we'll then talk about in a later slide. That will then send information to calculations in the Python script, and that Python script would also send information to the Capella sim, and that would, in tandem, pretty much move the simulation at the same time with our physical arm, and all the data would also be sent back to the PC Nucleo to our motor and motor drivers. So our knowledge on how to communicate with Capella came from the Capella Sim user manual. We came across something called 0NQ Melt API. Yep. The way Capella details it is it just connects external applications to the simulation. That can either be a robot or another Capella. We want it to be running at the same time, so I think we'd be running in stepping. We also read that it also includes all API functions for Python, but Python you have to include a plugin, I think, right?
You just write Python script.
Right, okay.
So this is the MATLAB. You're gonna fix MATLAB with Capella.
Yes.
Cool. You'll be doing M files from now. So not Simulink. Simulink doesn't talk to Capella, but MATLAB does. So you have to do MATLAB to Simulink. Connectivity, FYI. Cool. So we started off with the forward kinematics approach with the pH parameters, knowledge Hadoop. The code on the right looks very similar if you did the homework. We just modified it for our robot, which is using that code in the video that you saw previously. You could also include make it print out on the simulation positions of each joint. We also included in-between movements, so it doesn't hit anything while it's moving, so it would lift the y-axis intermediately. And what we're doing trying to do right now is trying to include the inverse kinematics approach. Capella does include something called an IK generator. It would generate a script for solving IK for the selected test. There is a lot of documentation on the Capella user manual, which we are going back and forth with.
So it looks like Anthony is going to be dealing with a lot of the API and the implementation of the code. I've gone ahead and written out a block there. And this is a block diagram, kind of just describing what the overall process between Capella and MATLAB we're doing together. So Capella, we're going to give it a target currently. We'll work on using maybe a camera in the future, but for now, we'll have like XYZ, and then it'll have the inverse kinematics, and then it'll pop out some thetas, which we'll send over to MATLAB. And then MATLAB is going to use those thetas in order to translate them into steps, because we're gonna drive motors, so we can't just use data, we need steps and voltages in order to know how much we're moving our joints.
Real quick, Jason, are you using MATLAB or Simulink?
We're using MATLAB and with Simulink and Coppelia.
Okay.
Yes.
Because technically you could almost do everything.
Yeah.
In MATLAB, you don't even need Simulink. So there's actually an STM driver, I think, for MATLAB directly.
Yeah.
So you can just write the code.
Yeah, we'll mostly use MATLAB language.
Okay. Cool. All right.
So yeah, after we get our steps, they'll just, here, this is where our feedback loop is. There's only the pressure sensor in there right now.
So how are you getting the position to give the inverse kinematics the location of the inverse kinematics?
Position for the inverse kinematics.
So you use that there's no cameras you're using, so how are you getting that work?
We're using the potentiometers we have scattered throughout our.
Okay.
Okay. So here's some pseudocode. Pretty much, so Coppelia is going to. Yeah, I'm not gonna go over that. I left this in just the base, just in case.
We're not there yet in class, so.
Okay. So basically, that's just to reinforce what is here currently on the block diagram. Yes. This is the code for it. This is easy to explain. This is just our loop for our sensor. Also, when we're doing our steps at the bottom, when we're generating them, we have to accumulate. We have like an accumulator because it loops through the code once, and that's a little too short of a time. It's just going to move like a little, so you just kind of want to account for stuff like that. Yeah.
So are you using MATLAB for the PID or are you using Simulink for the PID?
We're using MATLAB for the PID.
Yeah. So what is the Simulink doing?
Simulink is going to be providing.
Right, so you might want to look into the MATLAB libraries for the Nucleo.
Yes.
It has a lot of stuff built in already for you.
All right.
So instead of having to go to Simulink just for that, you may be able, I haven't done it yet, but I've only just read up on it. Hey, it has, I don't know what the support looks like, but you may want to try it, it may be there. So you may not have to even have that Simulink support for it, you just want to use MATLAB by itself.
Yes.
Got it?
And then here's our current timeline. We're around here, which is around about right. So, yeah.
Sounds good. Sounds good. I'll give them a hand. Questions for you guys? No?
Why did you do Is it recommended to add that capacitor to the power supply each driver?
Yeah, basically it's there to just prevent the current spike from breaking those A498s, or to help them last longer. Because technically, from what I remember reading, the A498s are supposed to only handle about 2 amps of current, and then if there's like spikes like crazy, well, like as Dr. Bosman just said, it burns out, right? So I just wanted to include that, so just, insurance, I do not want to deal with something coughing out in the middle.
Yeah, I don't completely completely understand the capacitor, because remember how when we took PCB design, capacitors were littered everywhere in like actual PCB designs.
So let me go through that now. Okay. So the little tiny 0.1 capacitors, those are decoupling. Imagine, remember, the higher the frequency, the smaller the capacitor is, turns more into a wire from an open, right? That's how it works. So that's a noise thing. So that's on the PCBs, we tend to use that for decoupling to get rid of the high frequency noise and shunt them to ground. In this case, it's acting as an energy accumulator. So when you get a large draw on it, that's when these will kick in. That's the idea behind it. It'll provide energy. Not a lot of current, but it's a very small amount, that very little, I don't want to call it inrush, because it's not quite inrush. But when you have those spikes, as you were calling them, it's going to give you a little bit more energy to not have that draw have to be unavailable. So that's the idea behind using the capacitors. Imagine you're going along a road, and all of a sudden you have a dip. The idea is that capacitor fills that dip in so that's nice and smooth. That's the easiest way to explain it in 5 seconds. Okay? Does that make sense? answer your question? Huh? Okay, any other questions? All right, yeah, you got another one.
If you ever worry about like inrush current within an inductor,
No, it's the inductance which is causing the inrush. So it's those windings and those steppers that are causing the inrush. It's like, because initially, that wire, there's nothing in there. It hasn't stored any magnetic energy to push back on it, so it's going to have basically the dead short.
Yeah.
It's like it's just a wire all of a sudden, because there's nothing pushing back on it, because there's no energy in that core yet. So it's going to come in really fast. So that's a massive amount of current, and so that's like the 4988. It's like, I can't give you that much current. I'm done. Sorry.
Yes, Andy, let's do this.
Sorry. No, I was trying to see if you could tell you. So I was wondering, why does that motor driver have any like switches or something like that to switch the amount of current they handle? Because at least for ours, right now, we have like different setups for the switches to actually handle different types of current. So I don't know if that's something you guys thought of already, or I'm just wondering.
Ours are like set. They're just like open-ended, like just straight up NEMA 17s.
So kind of going back, I forget. No, I think it's you guys who are not. You're not running the 4988s, are you? You're running the other ones. They're a little more robust. If you guys remember seeing Noah's presentation, they're a little more robust than the 4980s because they handle actually the spikes and all that kind of stuff. You get what you pay for. But so you know, I don't know if that answers your question, but you're not paying a lot of money for them, but you know, they get the job done.
Yeah, these are the cheaper ones.
Yeah.
Yeah, that makes sense. It's smart you guys asked for it. You know, smart.
Isn't that the data sheet?
Yeah, I don't know. Sure.
All right, any other questions? All right, give a round of applause. Good job, guys. All right, well, Danny's team setting up for our fifth and final presentation. I want to make a couple of comments on what I've seen so far. Set up.
I'm probably just going to throw it.
No, don't do that. Trash can's over there.
No, that's where I'm going to stand.
Okay. Are you sick?
I think I ate something big, bro.
No, I mean, it's not like nerves. It's
like, I woke up, yeah, probably. Okay. Nothing too bad. That's not.
It's not liquid food poisoning.
Just do it my breakfast.
Oh, okay, that's all. We've had a great graphic description on that one. You guys, each team member has definitely listened to what that feedback was from the last time we spoke, and when I sat down with all you guys. So I want you to know that I see it. Still a couple things here and there I noticed, but I'm not going to say them. I'll just talk to the individuals one-on-one if I remember. But by and large, everyone, you took the feedback to heart, and it shows. And so I'm really impressed with the presentations today. I mean, the first set of presentations were like, okay, no big deal. They're okay. Some of them were pretty good. But what I'm seeing today is you recognize by watching others and by critiquing others, how to make yours better while listening to the feedback that others gave you. And so that means you've grown immensely in your ability to present and articulate your designs, which is not easy. This will help you a long ways in your career. And so, again, as I said before, Friday is the due date. I'll put the link up there. It will be graded, but I will be grading what your presentation. You need to be taking notes on all your presentations, as I told you before. I will be grading those. Any questions on that part before we jump into Andy's presentation, Andy's teams? People are definitely projecting to the back. Everybody's talking. Everyone's sharing technical elements of the design. So again, those are some of the big feedback items for all teams. I'm really impressed with where you guys are at today. I'll wrap everything up after Andy's team's presentation. But overall, you guys definitely listen, and I think it's very important, and it's reassuring to see that you guys were able to do that and make those pivots. Okay, it's all you guys.
Hi, my name is Andy.
I'm Christian. I'm Caleb, and we are Team Armenheimer.
Why is Tony's name still on there? He's
our mascot.
Oh, parenthetical.
Our mascot looks like never here.
You should like put parentheses on it. Step one.
Sorry.
Okay.
So as of last time, we had a little bit of update for our mechanical design. So Caleb, you want to lead us?
Gotcha. So took the feedback, obviously. Our previous design was not going to cut it, obviously. It was more of our just primitive, like, just essentially how we were going to do it, kind of. Not really thinking more into the detail. But if we move to the next slide, we have our new design. We did end up using a reference. I think the guy's name was Evan Cacao. It was a hard name for them. But essentially, what we're doing is just swapping out our base because we still want to go with the planetary gearbox.
Did you guys do this drawing? This is yours, or is this their design?
This is their fully assembled. We're the only difference because what we're changing you can't really see because it's inside the base station.
If I may,
Yeah, go for it.
So what we're gonna do is we're gonna use that similar setup, but the inside's gonna be swapped out instead of using I think it was like the gear with another small gear kind of pulling it around like a band. We're gonna be using the planetary gearbox inside of that instead. So we're gonna swap it out just because we're really excited to use this gearbox to see how it would work. So.
My other question is like, because we're gonna go back since you haven't presented this yet, this is a new presentation. Does J joint one or joint the shoulder joint, that second one, is that gonna have enough torque to drive that?
Yeah, it should. We're gonna be using.
It should?
It should, yeah.
Okay.
It's gonna be probably about going to 23 or 22. Yeah, I started. Yeah.
That one will have a stronger stepper.
Yeah.
Also, one of the big differences that we're doing is we're changing out the pedals for the motors because we're using completely different motors. And then the same for the end effector. We're still doing a three-part design, which will show up in our next. So we have just another prototype of what we're doing for our three-front design. We are using TPU. Basically, we're trying to go for kind of like a rubber grip that helps with traction. We're still making some edits. We do plan on adding kind of more like teeth, so it has a better grip at the end. But yeah.
The idea is to wrap around that object and just this TPU is very
So this is our electrical schematic. We're going to use the laptop for the webcam and for the Nucleo. The potentiometers are going to be connected to the Nucleo as input for keeping the position tracking of the steppers. It's being powered by a DC power supply rated at 32 volts, 10 amps. We're going to have 4 total motor drivers and steppers. This is rated for, I believe, 40 volts, 4 amps. And the direction pulses will be taken from the nucleus as the output.
So that's for the sensors. We're going to be using potentiometers. This potentiometer looks a little bit different, but it's just a housing. If you open it up, it's just a potentiometer that's inside. For just ease of use, I looked at these, and they tend to have a little end that we can just probably put at the end of each motor that's driving the joints. So that way, when we turn it, we'll also rub the wiper along it, and as the little metal gear part will turn it. So very similar to, I think it was Team Speds. You guys use potentiometers as well, right? So we're going to use the voltage along the wiper, probably 3.3 volts, as you can see up there. And we're just going to measure the size or the voltage as it goes along, and that'll give us the angle. And that potentiometer has 270 degrees of rotation in it. It's not a full multiple turn, but it'll get the job done for what we need because we won't really need it to turn more into 70 at all. So as for the Logitech camera, I think those are pretty good for using with OpenCV. So we're going to use that one for what we're doing. We're going to use color tracking. So I think we just need to disable the setting in the camera that kind of muddles the ability to use color tracking. But other than that, it should be pretty good for what we're doing. Yep. We want to go to the next slide. Sorry, I'm not turning over. So for the motor driver board, so these are the nature of the motors. We at least need a driver that can use 3 amps. And the reason I was asking you, Jason, I know his name, sorry. This motor driver, I think a lot of other motors, like BLDC motors, have some sort of similar design where you can just flip the dip switches and it can give you different orientations. So as you can see right here, it lets you kind of adjust the current that you want to use it for, and you just flip the switches. So if you switch it switch 3, 5, and 6, you'll give you a certain current that you can use it at.
And I think these are the same ones you guys use, right? Yeah. And this is
you got 3.
This is what other teams have used in the past. They tend not to break, whereas the 4988s do tend to break. So that's why I just caution you all when you're using them. These tend to be pretty robust. This is an off-the-shelf, just plug it in and it works.
Yeah. But yeah, we have 4 of those connected to each of the stepper motors. We also have a servo motor, which we don't really need that for servo, obviously. But yeah, so you can use that to drive the stepper motors. Speaking of, we're going to go into stepper motors right now, which Wesley's talking about right now.
So quick recap on the steppers we'll be using. We're going to be using 3 of these 17 PMs and 1 of the 23s, which is going to be on that second joint you were talking about. I also found out that they were open loop and unipolar, so they have 6 wires instead of 4.
Does that driver support unipolar?
No, but so what I found is that you don't need to use the center tap that the 6 wires do, so it will work.
You can make it a quasi-bipolar.
Yes.
But I think you lose you don't get 1.3 per step anymore, is that correct? You still get the 1 point out of that motor?
You still get the full. When I was searching through the difference between unipolar and bipolar, I found that unipolar, it had, comparing between the two, the torque between the two is a significant difference. And you get less torque in the unipolar compared to the bipolar.
Right. But I also thought it might be 0.9 unipolar or 1.8 in the bipolar mode, or I don't know if it's 1.8 in the unipolar mode and 3.6 in the bipolar mode. You might want to check that.
Oh, okay, yeah.
Because you also give up step sets.
Yes.
So before we get into any of the actual specifics, I wanted to show the block diagram of how the Nucleo would connect to the different motors, motor drivers, what have you. So it all starts from the computer. From the computer, we're going to be using CubeIDE to write to the Nucleo. And from the Nucleo, it sends the control signals to the motor drivers, which in turn drive the motors. And all of them are, again, powered by the power supply. And then in order to ensure that they're at the position that we want, we're going to be using the signal pin from the potentiometer to feed back into the Nucleo. How exactly that looks like, I have yet to kind of hash out the specifics. And then from the computer as well, we're going to be connecting it to the camera, which we will be using Capella Sim in order to program the computer vision. And we're going to be taking the image data and then importing it into CubeIDE.
I think the block diagram needs to be updated, honestly. So the data from the computer, from the camera goes to the computer, and then Coppelia block needs to be in that computer, as well as the data image. And then that goes from, all that is in the computer, then goes to your cube. That goes to the Nucleo, which is going to be adjacent because that's the tool used to write the code. You don't actually send it to CubeIDE, which then sends it to Nucleo. CubeIDE is simply a tool to allow you to write the code for the Nucleo. So you really should update the diagram. So cube ID really doesn't belong in the block diagram. That's not a part of a function, that's a part of how. How do I look at it?
And is the general architecture, as it's kind of reiterated what I just explained in the last slide, but there will be sending the signals for the different motor drivers. We're going to be setting it to the step and directional pins. We're going to be using the general purpose I/O pins on the nucleo for that. And again, the position will be tracked with a potentiometer, and which we back into the nucleo, and it'll be the case for all of the base, shoulder, elbow, wrist. I don't think for the grips, because I'm going to have to do a little more research on that. That's going to be. And then the software, again, we're going to be using Cube IDE. We're going to be using the 76 7ZI. And we're going to be using Python to program the computer vision along with Coppelius. And then from the research I did, we're going to be using Coppelius to acquire the image data, which we then import into Python, where we then program the decision making from there. And it will help us recognize features and sharp edges or colors and things of that nature, which would allow us to have better control over the decision.
Give them a round of applause. Questions from you guys? Carlos has one.
Sorry, does Coppelius in process?
Apparently it does, because I cannot speak about using Coppelius before. There are vision sensors that I believe you use, and then those.
So the answer is yes and no.
So I thought they have I know they have simulator.
You have a simulated camera sensor, but you process that in your external or your Python script. The Lua doesn't really do that. So you're going to use OpenCV, or if you want to use MATLAB to do your image processing, you can feed that data into those elements. So Coppelia itself doesn't do it, but you can use Coppelia to use a synthetic camera to feed that into that script and say, hey, it works in my simulation, therefore it should work over here because it's going to be similar.
Sorry, to interject. It's like when the little tutorial that you showed us, you could switch to that other camera.
That's right. Oh, okay. And I can feed that data outward to my API, my external API, or MATLAB, or whatever I wanted to process it as though it's also my real data. So no, it doesn't, but it could be sent to be processed by something external.
Yeah, I forgot to mention OpenCV. My bad.
I did see online that Sim does have OpenCV.
Well, it has support for OpenCV through the Python API. Right. And you can do that either through the Python external API or through the Python code. I've never done Python into the Python script internal support for it, be able to import the OpenCV, but I think most of the people are using the external API, which we'll go over how to do that when we come back. Answer your question? I'd like to answer the form.
Okay, so when I run my OpenCV, I rapidly get data from the camera to.
Correct.
So obviously you see the terminal flipping.
Yeah.
So but if you're running a simulation while you're running that, wouldn't that be keep feeding the data to the simulation? Then
no. So that's what I'm saying. The simulation provides data to the Python script, not to the. You don't send the data to.
So what exactly the data is sending to the Python?
That would be the position. That would be the positions for the IK solver, is what I'm assuming. We have to extract them. So we'll get into that when we come back. Yeah, that's when we get it all the software. So for you guys to be able to get to that level, you have to have all your electrical working, your motors working, and everything's kind of and then you're working on your software in the end. That's why I'm pushing you really hard if you're going to go down that route to be where you are today, so that we have software in that last month. We're not sitting there trying to do software in one day. That's too hard. We've allocated, if you notice, it's been 1 month of conceptual design. It's kind of like understanding how to spell robot arm. Then you've done a month of mechanical, 1 month of electrical, and we'll do a month of software. So it's a 4-month process to get this done, which is kind of crazy. Before I jump into anything else, are you guys done? Is that it? Any other questions? All right, go ahead. So many of you are probably in senior project now, yes? And you are probably looking at this project at the same time, and you realize you've done an entire senior project in the course of 4 months, 4 months, which is crazy and impressive at the same time, right? And it will get there, trust me.
I just thought they had a question. I'm gonna turn this.
Again, the trick is to not get stuck in these traps of ask yourself, what am I trying to do? Because you can convince yourself by drinking your own bathwater, as we've said before, you can convince yourself you're right based on assumptions which are inaccurate, which was the premise of that exercise I gave you guys of draw a square using 3 straight lines. And all of you made the assumption that it had to be a shape. I never said it had to be a shape, ever. So Michaela, I think, said think outside the box was, I think, what was, that's kind of the idea, maybe it was Wesley. You think outside the box, but it's more than thinking outside the box. You need to always be self-critical of what you're doing. So as you've done the criticality assessments on your presentations, you need to do that on your work as well as the engineer, the technical work. Constantly ask yourself, does this make sense? Am I solving the problem I think I'm solving, or am I solving something else? Are the barriers that are in place, are they valid? Or am I assuming them and they don't need to be there? So on a lot of your designs, I see the chance to get into that trap, but I don't see you in that trap yet. But be mindful of it in the coming weeks so that you don't get stuck in that trap. Because when you get stuck in that trap, it's a time sink. And you can't make up that time. It's a schedule that you can't slip. So I mean, that date's that date when we do the presentations, when you guys do the demos. But in the workplace, it's very, very common too. I see engineers fall into that trap constantly. It's like, well, we're going to do it that way, right? No, why we do it? Because why? Because I said so. Because that's why we've always done it. But that's not an answer. If that doesn't make sense, then don't do it that way. And that's where I see most of them, because we've always done it that way. But why? Why? I don't know if you ever see my car. My car. My 2003 Tahoe I still drive because the engine's amazing. My license plate says "Why ask why."
Yeah, it does.
Yeah, it does. Why AZKY? Why ask why? Because I always question my assumptions. Always. It's which have given me the opportunities of Boeing to be at that design engineer, to be that pain in the ass to a lot of people too. Why keep asking these questions? Because I need to find out, is that a legitimate requirement? Do I have to do that? What is the fundamental problem that I'm trying to solve? Why am I approaching it this way? And is it good? Is it the right way? I'm asking myself that constantly when I'm doing designs. Constantly. Is this the right? Am I really getting to the essence of the problem I'm solving? Or am I masking it by some preconceived assumption that's not valid? In other words, do you have to draw a shape to solve the problem? I never said you did. Looking at things from different perspectives constantly will give you a different take on it. Walking away from it if you need to. Sometimes when you get stuck in design, you're like just tunnel vision. Walk away. Go for a hike. Go work out. Do something physical. Do yard work. That's the other thing I used to always do, still do. Mow the lawn, right? Doing something physical, your brain will subconsciously sit there and stew on it and chew on it for a while. And then you come back and it's like you have more clarity. If you just jump in and do it, done, you totally missed it. You're in tunnel vision mode. You got to wake up, look around, and as you're doing this physical exercise, you're going to probably be thinking, well, do I really need to do this? And you're like, oh, I don't really need to do that. Oh, this is a better approach. When you talk to your team partners, you will have that same opportunity. And this is where you have to be critical of your team members, not to drink the bathwater. Don't let somebody convince you they're right if it doesn't sound right. be critical, but in a positive way, professional way. Don't be mean. Don't be like, what a piece of junk design. No, be positive. I mean, be constructive. But also, on the other side, be willing to take that constructive questioning. Because when you go to design reviews and they ask you questions, and they're especially within the company, your managers or your superior engineers, they might ask you questions. They're not attacking you personally. It's constructive. They want to make it better, and they're probing. They're probing to make sure that the design is a solid design, as you guys should do with one another in your own team. Keep each other accountable, and make sure you're not assuming things are not valid. So that was the point of that exercise to begin with. Wasn't meant to frustrate you. It was meant to make you have perspective. Don't assume. Don't drink the bathwater. Okay? The other thing you want to do is throw the baby out with the bathwater. That's another expression that I love to use too. Throw the baby out with the bathwater. We throw everything away when there's actually good things inside of that we're throwing away.
Don't throw the baby.
No, don't throw the bathwater. Make sure the baby's in there. Not in there. All right. Any questions for me about what's coming up?
Yes.
What's up?
You said you're going to talk about the simulation.
Yes. So when we come back, I should have the robot arm up and working. I got some new parts that maybe improve the design, so I can showcase how that all works together. I'll be using the Robotis. It uses PySerial. And we'll go through how Robotis' protocol looks. It's a very thick protocol compared to what you guys need to do, but it's also a much more involved a device. It uses external API. It's talking to the Coppelia Sim using Python, using the external API. I'll throw some computer vision in on that as well. We'll do some IK with it. So I'll be able to show you guys some approaches. It's not the only approach, but it's an idea to kind of like where you're going with all of it. I'm not going to necessarily say, here's a square, go to that square. I'm not going to give you that answer because I'll make you guys work on that one. Okay, that's fair, right? But I will give you the starting points on how that Python external API talks to Coppelia, talks to PySerial. Maybe you're going to use a joystick or keyboard commands. Don't use Pygame. There's a caveat if you're using Coppelia Sim. You can only run at the rate of the simulator. Okay, that's one caveat. It's not a bad caveat, but if the simulator is doing the IK, you're going to go in the external Python is going to step the external simulator, or it's going to externally step the simulator, so it has to run in lockstep. The Python code and Coppelia run in lockstep with one another. It could be MATLAB or Python, it doesn't really matter, but they run in lockstep. So that, remember we talked about the engine, the Dynamics engine, the MuJoCo, that has to be stepped. That step is being told to step from that external software. So it says, I'm going to do all this stuff, computer vision, blah, 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 blah. I'm going to send the data maybe to Coppelia. Coppelia, okay, step the next iteration and go through and step those iterations. So that is one of the caveats. It's not a bad caveat, it's just a caveat nonetheless you have to be aware of. So we'll go through that stuff when we come back from spring break. Okay. I will go over computer vision as well, but I won't do that the first time, that'll be the second time. If you're doing computer vision, you're probably already doing that on your own, so it's really more for everybody else, and to fill in some holes that you might have had on your own. If you're using PixieCam, basically everything's going to be built into the PixieCam. The computer camera, if you're not using computer vision for your code, and no one says you had to, okay, you do have to have teleoperation though. So teleoperation says, I have a webcam that I'm looking at on my computer, I'm driving it. That may be all you're doing. So if you're not using computer vision to solve the problems, you still need some way of seeing what your computer arm is doing, either mounted on the arm as a point of view or something just sitting there on a little tripod or on the camera or wherever that you are controlling. So you're not looking at this. I actually make you turn 180 degrees away so you can't see it, and then you have to drive the robot with the teleop, however you choose to do that. Then we flip it around and you can actually say, okay, oh, I see what's going on. It becomes more of a game mode kind of thing. Okay. So leads, here's what I want you to do. Are we doing autonomous control? Yeah, one says yes, and if he gets it and he shows that it works, he gets the bonus points. If it works. If, okay? Other than that, the two required are teleop and remote, okay? Building the walls, 100% autonomous. No remote controls, no teleops. Push the button and go. Right? Now, correct me if I'm wrong, I have two teams who have the attack advantage, right? Charles and, no, you guys, right? Because you guys were late. You didn't have it when you had to, right, Jason? Yeah. So you guys get an extra attack ball, right? That's what we said was going to happen. When we come back, you're going to show me, you're going to have me do the demo because we haven't done Jacobians yet. But when we get done with the Jacobians, you use Jacobians with the simulation that you've done. That's going to give you 2 additional advantages, right? So one's going to be time and one's going to be extra blocks. Leads, I want you to think about what that extra block is. I want you guys to come up with it amongst yourselves. So when we come back from the spring break, that lecture on Wednesday, you're going to tell me how that's all going to play out. So you guys Discord, however you all want to message each other, and get that dialed in. That's your job as your leads.
I saw we don't have a time limit.
We don't have it, that's TBD. So we're going to want you guys to address all those TBD time limits amongst yourselves. You guys tell me what you've come up with. Sound fair? I'm thinking like 3 minutes, kind of in that ballpark. William?
I thought it was that we didn't choose the time, and that's why I'm sure that we limited number of shots.
No, for the other ones. No, for the build time. Build time. What's the? I don't. The sooner the better for your own benefits. So ideally, it's when we come back. But we could do the week after that. Anything after that, you're too late. So you need to have an internal deadline of one of those two. I would recommend one of the two, but I mean, if half your team's gone to Hawaii for spring break, plan accordingly. That's all I can say. Any other questions? Comments? Concerns? All right, I'll see you guys in lecture.
Professor.
Yeah.